Okay, in this video, we're going to look at the most important of all alpha carbonyl substitution reactions, the aldol condensation. Okay, all right, so here is the aldol condensation. We're going to take two molecules of the simplest aldehyde that has alpha hydrogens. Okay, so here's the alpha position. And we're going to treat it with base at room temperature. What you're going to find is that two of these molecules get together to make this type of compound here called the beta hydroxycarbonyl compound. Okay, and let's look at the mechanism for this reaction. Okay. So recall that alpha hydrogens of aldehydes and ketones has a pK of around 20. Okay, so hydroxide ion isn't quite strong enough to completely pull this off, but it is strong enough so that there's going to be an equilibrium established here. Okay, so we're going to remove the alpha hydrogen, and we're going to get the enolate. Okay, and the enolate, an important resonance structure is this resonance structure here, which we're going to call the carbanion resonance structure. And you'll notice here that this is a nucleophile, and when we looked at the chemistry of aldehydes and ketones, we saw that they were reactive to nucleophiles. Okay, so this anionic or this deprotonated acid aldehyde, this anion, is going to react with another acid aldehyde molecule that has not been deprotonated. And it's going to now make a new carbon-carbon bond. This carbon-carbon bond right here is made through this set of arrows. Okay. And once this anion is made, it's going to react with the water and just produce this product right here. Okay, in this reaction here, we're going to call this partner the aldol donor. Okay, and this is the aldol acceptor. Okay, this is a name reaction you have to remember, the aldol condensation, but there's no person named Aldol. Okay, it's just an aldehyde making a compound that has an alcohol and an aldehyde in it, and in the simplest equation right here. All right, so this is not the best resonance structure, this carbanion resonance structure, but I like to emphasize that I'm going to use it because the diagrams are much cleaner. There's more arrows when I use the enolate resonance structure. So we get right down to the crux of the reactivity when we look at the carbanion resonance form. Okay, the beta hydroxycarbonyl compound is not stable in strong base. At higher temperature, it reacts to lose water. Net result here is minus water. And it makes this type of compound called an alpha-beta unsaturated carbonyl compound. Okay, this reaction is actually quite favorable because of it makes a conjugated system. Okay, and how does this occur? Okay, you may remember that we can take alcohols and turn them into alkenes by eliminating water, but that reaction for simple alcohols doesn't use base, it uses acid. So this reaction is mechanistically quite different. Okay, so here's what's happening. Hydroxide ion at higher temperature is pulling off the alpha hydrogen here. And it's important to note here that a lot of things can happen. You could also pull off this one, and you could make a hydrate, but none of those really leads us in the right direction. Okay, so because we can make this stable anion, it can now do a process which we call a beta elimination. and forms the alpha-beta unsaturated carbonyl compound. This type of elimination reaction, we call it an E1CB, where the CB stands for conjugate base. Okay, so it's kind of the opposite of this one. That when we have the acid, we make a carbocation. When we have the base, we actually make an anionic carbon. Okay, and we do the elimination in the second step instead of in the first step. Okay, or the actual bond breakage occurs in the second step instead of, I guess, in the middle step of the classic dehydration. Okay, all right, so this is a fairly general reaction. As long as you have an alpha hydrogen, you can do this reaction right here. Okay, and if you want to do the higher temperature reaction that generates the alpha beta unsaturated carbonyl compound, you have to actually have two alpha hydrogens. Okay, so we got rid of one of them here, and we got rid of the other one right here. Okay, so to make the more do the aldol at higher temperature with the water elimination, you have to have two alpha hydrogens in your starting material. Okay, so the reaction proceeds in higher systems. Okay, here is phenyl propanal. Okay, so KOH at room temperature, it produces the aldol product. Okay, and important thing to note, here is our aldol donor. Here is our aldol acceptor. And the new bond that we form is the alpha beta bond. Okay, at higher temperature, this one can undergo the water loss just like the other one and produce the alpha beta unsaturated aldehyde. When ketones do the aldol, this reaction at 25 degrees C is not quite as favorable. It's hard to really make this one go in a high yield. Okay, but the reaction at higher temperature actually is favorable because it produces a much more stable compound. So the ketones can do the 80-degree aldol, but in some cases they can do the 25-degree aldol, but in most cases this one is really not all that favorable. Okay, what if we have two different substrates reacting? And this is called the mixed aldol. It's an inherently messy reaction. Let's imagine that we're taking these two aldehydes and we're treating them at KOH at 80 degrees. All right, we can have this alpha carbon making contact with that carbonyl after this is deprotonated. After this is deprotonated, that could make contact with that carbonyl, and this leads to two different mixed aldol products right here. But if these are in here together, there's nothing to stop one of these from combining with itself. Okay, so not only do you make these mixed aldol products, you also make these two self-aldol products as well. So this is a reaction that really sucks. Okay, it's very complex. It's got making a lot of products. You wouldn't want to do a reaction like this. This is poor planning is what we could call this reaction right here. Poor planning if you wanted to get one of these compounds. If you set out to make a mess in the beginning, I guess you could call that a great plan. Okay. Under some cases, however, the mixed aldol can be quite efficient. Okay. If one of the partners contains no alpha hydrogens, then the mixed aldol reaction becomes actually quite facile. Okay, so here is benzaldehyde. All right, so let's draw benzaldehyde out here. Here's the alpha position. And there are no hydrogens here. Okay, so we cannot use benzaldehyde as an aldol donor because it doesn't have any alpha hydrogens. Its only role can be as an aldol acceptor. Okay, so if we take cyclohexanone and benzaldehyde, combine them, if we are very careful to use only 1 mole of benzaldehyde, we'll get this product. But important thing to note is that we have an awful lot of acidic hydrogens in cyclohexanone. Okay, sorry, I have to put it there because it's off the screen. So we could actually add a large excess of benzaldehyde, and we would expect to make this product here if we had 2 moles of benzaldehyde. Okay, the condensation of this compound, I guess it's 4-heptanone and formaldehyde. We're going to react this to 25 degrees C, and we could expect to form primarily that aldol product, because again, this has no alpha hydrogens and it can be an aldol acceptor only. Okay, and since this is an aldehyde, both of these are aldehydes. They're more reactive than ketones, so the self-aldol doesn't really compete with the mixed aldol in this case. Okay. All right. So there's another case where you can have. Let's go back one. Okay. One of the partners contains no alpha hydrogens. One of the partners is vastly more electrophilic. These two actually are kind of fit both categories here. And a third category is where there's a strong thermodynamic preference for one partner over the other. Remember that when we look at the mechanism, all of the arrows were pretty much equilibrium arrows. So this is what we call a thermodynamically controlled reaction. We're trying to make the most stable product. Okay, and this is most common in intramolecular systems. Okay, if we take the compound here, there's several aldol possibilities. Okay, I'm going to label every alpha position. Okay, and if you note, all of the potential aldol condensations, okay, we have 3 alpha positions, and when one of those alpha positions is used as the aldol donor, the other carbonyl is going to be used as the aldol acceptor. Okay, so this arrow here is going to make a 4-membered ring, right? 1, 2, 3, 4. This arrow here is going to make a 4-membered ring, and this arrow here is going to lead to a 6-membered ring. All right, so these 3 compounds here are our choices. Okay? And a long time ago in organic chemistry, we learned that 4-membered rings are not nearly as good as 6-membered rings. So we would reasonably expect to produce only this compound in reasonably high yield. Okay? All right, let's look at this intramolecular aldol here. This is a symmetrical compound, and what we see here is that we have a lot of potential aldol condensations. Okay, I've only shown 2 of them, but every one of these alpha positions is equivalent. This compound has a plane of symmetry. It's a little hard to draw a 10-membered ring except as 2 carbonyl compounds. I'll just draw kind of a screwy drawing here so you can see that. All right, so here's our plane of symmetry. Okay, so every alpha position is equivalent. So when this one is treated with base at high temperature, you can reasonably expect that it's going to do the intramolecular aldol condensation. And if you look at the distance between the alpha and the carbonyl group, it's 1, 2, 3, 4, 5. So it's going to form a 5-membered ring fused to a 7-membered ring. Okay, this one here, this last one, it's also symmetrical, but here's the plane of symmetry here. So that those two alpha positions are equal, and these two here are equal. Okay, all right, so the two aldol products that we can form here are both 1, 2, 3, 4, 5-membered rings fused to 7-membered rings, or a 3-membered ring fused to a 9-membered ring. And if you recall, well, you've known for a long time that 3-membered rings aren't particularly stable, especially with double bonds in them. So it's very unlikely that the product on the right would form to any great extent. Okay, so these are the basics of the aldol condensation. Students have a little bit of a hard time seeing the aldol because a lot of things happen in the mechanism and the molecules grow to a very large size as a result of the aldol condensation. So we're going to end this with a few problems, but I'm just going to say one other thing about the mixed aldol condensation. An alternative way to do this is to do a directed aldol condensation. Okay, and here's how we do a directed aldol. We're going to actually perform the deprotonation steps and the aldol addition steps in two separate events. We don't actually have to isolate anything. If you're doing the reaction, what you do is you just have the ketone, you add the base, wait a few minutes, then you add the aldehyde later. Okay? And usually the second one is an aldehyde, sorry. Okay, so what we're going to do in step 1 is we're going to deprotonate with a base that's strong enough to completely deprotonate ketone number 1, the aldol donor, and we're going to do this process at low temperature so that there's no competing self-aldol reaction before all the base is added. Okay, so we have to use a base strong enough so that the reaction goes to completion. And after 1 mole was added, we don't have any free ketone left to do a self-aldol. Okay, and in step 2, we're going to add the aldol acceptor. Okay, so let's analyze this problem here retrosynthetically. Remember that you're always making the alpha beta CC bond when you are doing an aldol condensation. Okay, so there's our aldol donor. It's the one that has the alpha carbon as part of its makeup. There's the aldol acceptor. It's the one that has the beta carbon as part of its makeup. All right, so how would we do this? Their synthesis is going to require these two reacting partners. So we're going to take the aldol donor, deprotonate it to get the anion. Okay, we're going to do this at low temperatures and add 1 mole of this so that no self-aldol is competing, and then we're going to add the aldol acceptor later, and we can expect to get this. All right, notice here also that we made a couple of stereocenters. This is a more advanced topic. I urge you to take a class in organic synthesis if you're really worried about whether you make the compound where methyl and OH are on the same side or on opposite sides, but that is an issue that you can control, but we're not going to discuss it in this class. Okay. All right. So the last thing in this video is just a bunch of problems. You should solve them yourself by pausing the video, but I'm going to just go through them. All right, what's the aldol product here? When you see two here and just one substrate, it's usually a self-aldol. Okay, so if we treat this compound with KOH at 80 degrees, 80 degrees is the approximately the boiling point of ethanol. I think it's actually 78, but we just say 80. All right. So in this case, we're taking the alpha carbon of one cyclopentanone and it's contacting the carbonyl carbon of the other and eventually making the alpha beta unsaturated ketone that you see here. All right, the next one is a mixed aldol. An important thing to note is that this partner has no alpha hydrogens. Okay, and so we're going to do the aldol, and this is the product we get here. Notice that we have a lot of alpha hydrogens, but we don't react on this side right here. Because to make the alpha beta unsaturated ketone, you actually are removing two hydrogens from the system here. So both of these hydrogens here and both of these hydrogens that I just circled are being removed in the process of making the alpha beta unsaturated ketone. Okay, so it only happens on the side that has two alpha hydrogens since we're doing the reaction at 80 degrees. All right, the last one is an intramolecular aldol, and there are actually two distinct possibilities. Okay, we make this aldol by reacting the methyl, by coupling the methyl group with this carbonyl, and we make this aldol. Okay, so this arrow here is the one giving this one. This other one is we're taking this alpha carbon here and adding it to the methyl ketone. So that arrow right there gives you the product here. All right, so this it's hard to predict whether you would get one or the other. I'm guessing that this would be the major because it's the more substituted alkene. And if the whole system is at equilibrium, you should see that as the major product. But I would not count on that. All right, let's do some more of these. All right, so here's another self-aldol. We're going to take this aldehyde and do the self-aldol in refluxing ethanol. And this is going to give us the aldol dimerization product, and note that in the aldol dimerization product you have to have twice as many carbons as you did in the starting material. Okay, let's just verify that. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. All right, the next one is a directed aldol. Notice that this side of the ketone here has no alpha hydrogens. So therefore, we're going to deprotonate here. Okay, and the product we're going to get is this product right here. Okay. All right, the next compound we're going to use is actually a very acidic compound because these hydrogens here are stabilized by two different carbonyl compounds. This has a pKa of about 11, or about 10 or 11. So this is a very acidic compound. When we do the aldol condensation here at reflux, we should get the product that shown here, or again, This one has no alpha hydrogens, and it's the aldol donor. And those carbons of the aldol donor show up there. Okay, and this one, we can make two different compounds. Okay. All right, so we can take the alpha carbon there, and this gives us a 6-membered ring when it adds to that carbon. Okay, and we can take this one here, and this gives us a 1, 2, 3, 4, 5. Yeah, 5-membered ring over here. Okay, and gives you the product there. These look kind of similar, but if you look at them, study them for a few minutes, you see that they're actually structurally different compounds. The cyclopropane is next to the ketone in the compound on the right, and it's next to the alkene in the compound on the left. Okay, there's two arrows I had already done in my slideshow. I didn't even need to show them. Okay, here's a retrosynthetic problem. Predict the precursor compounds required for each aldol product. Okay, the important thing to note is we have to identify the bond that we're going to make, and that's the bond between the alpha and the beta position. Okay, in each of these. Okay, that's the alpha, and this is the beta. Okay, so those have to be in two separate molecules. Okay, so remember, the alpha side is going to contain our aldol donor, and the beta carbon is going to be in our aldol acceptor. Okay, so this first one would involve using this as the donor, and that's going to contact that carbonyl and the aldol acceptor. Okay, the second one is the result of an intramolecular aldol condensation. Note that when I break the alpha-beta bond, that the molecule still has a connection between beta and the alpha, okay, this bridge right here. Okay, so this is the precursor that you would need here. You would need a molecule that has both a ketone and an aldehyde group in it. All right, and finally, let's look at this last one. This requires, this is the donor right here, all of these carbons together. And this one, simple, I guess, thiophene carboxaldehyde as our aldol acceptor. Okay? And again, notice that in all cases, my aldol acceptor has no alpha hydrogens. Well, this one does here, but this is realistically the only aldol you can do is the one here that makes a 6-membered ring, and this one, again, no alpha hydrogens. So we can expect a very efficient mixed aldol condensation in the first and third case, and the efficient intramolecular aldol in the second case. Okay, this last problem is a roadmap problem with a spectroscopy question at the end. Okay, so identify A, B, C, D, E. Well, gee, what happened to the letter F? Okay, G and H. Okay, sorry, I left out the letter F here. Okay, so let's think about these. These involve some older reactions. Okay, so the epoxide is going to react with methyl Grignard. We're just going to think of this as methyl anion. Okay, so that's going to open that. It's going to proceed with stereochemistry to give us the trans alcohol. PCC is going to oxidize our alcohol to a ketone. Ethyl magnesium chloride is going to add to the ketone to give us this. Sulfuric acid and heat is going to eliminate water to give us the more substituted alkene. That's that one. Cleavage of the carbon-carbon double bond with either ozone or osmium tetraoxide sodium periodate is going to give us the diketone. Okay, and this is where we're going to finally, in the last step, do the aldol condensation. So the products that we can get are these two products. And again, we can make 6-membered rings by taking anion here and adding it to that carbonyl, or a 6-membered ring by taking the anion at the methyl group and adding it to the other carbonyl. Okay? The first arrow set A, gives us this product. Arrow set B gives us this product. Okay. All right, so what's the major product? Well, look at the spectral data. B has an alkene hydrogen in it. A does not. A also has the spectrum also shows a lot of 3-proton singlets for methyl groups. Let's get rid of A and B. Sorry, let's go with G and H to match that. Sorry. G is major. The spectral data here matches this. It does not match this. Okay, we expect that to be at 5 to 6 ppm or something like that. Okay, so that's not there. All right, so I think this is the last of the aldol condensation slides until we look at the Claisen condensation, which is the next one. So I'm going to stop the video right here.